My name is Joseph Mwiti Marangu. I am presenting. I'm a lecturer at Meru University of Science and Technology in Kenya, and I'm presenting part of the ongoing work on crack remediation of concrete. And for this particular paper, the topic is the effect of Bacillus Subtilis on crack remediation in thermally degraded limestone calcined clay mortars. The problem in crack is faced in day-to-day construction activities. Regardless of the type of cement that you use, you realize that cracks appear and they are actually inherent in concrete. Some of the causes of cracks is due to the heterogeneity of concrete. During the setting of cement, if proper curing is not done, then due to the heat of hydration that is generated, then micro cracks appear. Cracks also appear due to shrinkage, alkali silica, as well as due to mechanical loading or stress, and at some point also due to thermal exposure. When concrete is exposed to elevated temperatures, you find that micro crack, and these cracks actually are costly because they call for repair and maintenance of the structure, which raises the cost of maintenance. Also, the structural integrity of the structure is compromised, and therefore there can be failure or collapse. In some cases, the total collapse of the structure, leading to loss of lives and even economic losses when collapse of the building occur. There has been a number of attempts to heal the cracks in concrete, and some of them include the use of structural epoxy, resins, use of silica fume, among many other interventions. However, you find that some of these methods are a bit expensive and at times not environmentally friendly. The approach that is gaining a lot of researchers' interest at the moment is the use of microorganisms such as bacteria to repair and seal the concrete cracks. In this study, the focus was to use Subtilis, Bacillus Subtilis, to remediate the micro cracks in concrete. Basically, to reduce the cracks in concrete, we looked at introduced the cracks through exposing the material at elevated temperatures of 1000 degrees Celsius. And when any material is exposed to these temperatures, you realize that there is deformation which occur, cracking, sparring, and even strength loss. And when in the structure, you find that the structural integrity of the building is compromised, and therefore it can lead to the collapse at the worst case. The approach that I took in the study is I focused on using the newly developed limestone calcined clay cement, and of course using the commercial Portland cement as the control cement. Now, mortar prisms were made using both limestone calcined clay cement at a water to cement ratio of 0.5. They were cured for 28 days. Half of the 28-day cured mortar prisms were thermally degraded by heating them at a temperature of 1000 degrees Celsius in a furnace. Of course, this was to reduce the cracks, while the other half was used as a control. Now, both cracked and uncracked mortar prisms were subjected to compressive strength. porosity, and accelerated chloride ingress. In addition, half of the cracked and uncracked mortars were immersed in a bacterial solution containing Bacillus Subtilis, while the other half was separately immersed in curing water until the 90th day. Compressive strength, porosity, and chloride ingress were also repeated on the 90th day. In addition, microstructural changes in cracked LC3, that is limestone calcined clay cement mortars, were carried out using a scanning electron microscope before and after immersion in bacterial solution. So basically, the image that we see here is one of the images that you obtained in the lab when using Bacillus subtilis. You find that the bacteria is motile, as you see in the image. We noticed that from the study that the compressive strength at 28 days of curing, uncracked mortars exhibited higher compressive strength. The C is for cracked, while the UC is for the uncracked mortars. You realize that for the cracked mortars, they showed the lower compressive strength at 28 days, while the uncracked mortars showed higher compressive strength at 28 days. That shows that the cracks actually result to reduction in compressive strength. Again, when the mortars were immersed in water until 28 days, the cracked ones actually again showed lower compressive strength, while the uncracked showed higher compressive strength when cured in water, and this is attributed to autogenous healing of the mortars due to residue cement we hydrated, and when hydrating, then it could have resulted to gain of strength. When the prisms were subjected to or cured in a bacterial solution for 90 days, you realize that they both cracked and uncracked mortars. The cracked mortars, which and earlier exhibited lower compressive strength, significantly improved their strength, and from the study, it was shown that there was no significant difference in terms of compressive strength for both cracked and uncracked mortars. This shows that the bacteria has a higher potential to heal the cracks as compared to water, which is basically causing the normal crack healing. From the study, it was interesting to note that LC3 was not much affected by the presence of cracks, and this can be attributed to the presence of limestone, which acted as a filler material in the mortar matrix. On porosity, from the study, it was evident that after 28 days of curing, the uncracked mortars exhibited higher. The uncracked exhibited lower porosity, while the cracked one exhibited higher porosity. And this can be attributed to the fact that when cracks appear in concrete, the cracks form pathways for ingress of materials, and such as water, or they become the pathways for water to penetrate into the concrete, and therefore the material becomes quite porous and due to increased permeability. after 90 days of curing in water, the material became less porous, and again, this can be attributed to the fact that the material was gaining more strength with time due to the hydration of the residue material that could still not have hydrated at 28 days, and therefore water could have caused the residue cement to hydrate, and therefore there was a gain of strength. However, on the other side, if for the materials which were exposed to bacterial concrete, you find that they exhibited high, the lowest porosity, and this can be attributed to the stronger healing capacity in which calcium carbonate is precipitated by the bacteria and fills the pores in the mortar matrix. And when the pores are filled, then the porosity the material becomes less porous. So from this study, it is clear that the uncracked concrete, the uncracked prisms didn't show the lower porosity, while the cracked samples and higher porosity. On the other hand, the samples which were cured in water and the higher porosity as compared to the samples which were cured in bacterial solution. And the difference can be attributed to the fact that in bacterial solution, we have got precipitation of calcium carbonate from the bacteria, and therefore it results to sealing of the cracks. And when the cracks are sealed, the material becomes less porous. The chloride ingress test that was conducted, the mortar prisms were cast and subjected to accelerated chloride ingress. After the exposure to the chloride media, the mortar prisms were sliced into portions of 1 millimeter each, and the amount of chloride in each piece of mortar, the chloride was analyzed at the core, and the chloride profile was made using the fixed second law. And one of the samples, one of the error fitting curves that was obtained is what we see in the graph here. The apparent diffusion coefficient that were obtained from different samples is shown on the table here. At 28 days of curing, the limestone calcined clay, which was cracked, showed iron diffusion, apparent diffusion coefficient, while the one which was uncracked showed lower chloride diffusion. And the difference can be attributed to the fact that when cracks are present, the cracks form pathways for ingress of chlorides. On the case of OPC, we find that OPC with that and the cracks showed higher apparent diffusion coefficient than the one which did not have the cracks and cracked one. In terms of the nature of the cement, it is clear that the LC3 was shown lower apparent diffusion coefficient as compared to OPC, and the difference could be attributed to the fact that ordinary Portland cement has got more is more porous due to the fact that it, in its hydrated form, it has got calcium hydroxide, which makes it structure, its hydrated matrix quite porous. While in the limestone calcined clay, the material is more dense, and due to the pore refinement caused by the presence of pozzolanic clays and also the filler material that is limestone. Now, when these samples were cured for 28 days, for 90 days in water, we realized that the uncracked one again showed the lower compressive lower apparent diffusion coefficient than the cracked mortars. That is for the case of limestone, calcined clay cement. And a similar observation was made when OPC was used. When we compare the mortars cured after cracking at 90 days in water and in bacterial concrete, you find that the one which was cured in bacterial concrete exhibited lower apparent diffusion coefficients, and this is a clear indication of the pore refinement that occur as a result of the bacteria precipitating calcium carbonate, hence filling the pores in or the cracks which might have been present as a result of heating the samples at elevated temperatures. Generally, it was observed that in both cracked and uncracked mortars, when the bacteria solution was used, there was no significant difference in terms of apparent diffusion coefficient, and this shows that that the bacteria is quite good or efficient in terms of healing the cracks. When microstructural studies were conducted, the first image we took one sample that is for limestone, the calcined clay, which and the cracks, and the cracks were quite visible when before they were visible in using a scanning electron microscope. After the samples were immersed in a bacteria curing solution, there was a degree of crack healing, and it was again quite clear that the cracks in terms of their sizes are actually greatly reduced after 90 days. And this shows that there was some deposition of calcium carbonate that were visible due to bacteria precipitation process. In conclusion, Bacillus Subtilis solution showed higher potential for self-healing than water. Uncracked mortars exhibited higher compressive strength, lower porosity, and lower apparent chloride diffusion coefficient than cracked mortars at 28 days of curing. And this mainly can be attributed to the fact that cracks destroy the calcium silicate hydrate gels, which are mainly responsible for strength in cementitious materials, and also they create the voids in the pore network of hydrated cement, which affect porosity. And the voids act as pathways for increased permeability of aggressive media such as chlorides and even water. At 90 days of curing, the compressive strength, porosity, and apparent diffusion coefficient of cracked mortars.
Excuse me, so maybe we can fastly conclude because to respect the time. Thank you.
Okay, thank you. At 90 days of curing, the apparent diffusion coefficients were equivalent to those of uncracked, and this is mainly due to microbial action. The microstructural examination of mortars showed visible cracks, and the thermal treatment which healed as a result of calcite deposition after curing in bacterial solution. And in conclusion, lastly, is that Bacillus Subtilis was found to improve the crack healing capacity of thermally cracked mortars than water. I wish to acknowledge the funding from the Kenya National Innovation Agency and the Meru University of Science and Technology, as well as the Center for Materials and Technologies. Thank you very much.